So thanks very much to the organizers for inviting me, and thanks for you for staying for the final innings. So I like this conference very much because I think it used to be that the quantum information thermodynamics people were having their separate conferences, and the stochastic thermodynamics and other communities were having separate conferences, and it feels like more and more there's conferences where both communities are together, and so instead of criticizing each other's paradigms and definitions of entropy from afar, we can now do it in the same room. So I certainly welcome any kind of discussion or questions or criticisms of the underlying assumptions. So I'm happy to take questions on that. So this is joint work with the UCL group, Alvaro Alhambra, Luis Massanes, and Chris Perry, who's now in Copenhagen, and Alvaro, who's now at Perimeter Institute. And I'll be talking about two things. One was the initial thing, which was about majorization and fluctuations. And I guess it was a kind of a realization at some point that the kinds of things we were doing in quantum information thermodynamics was related, how it was related to what people were doing in stochastic thermodynamics. So at some point we realized actually the paradigms are very similar, although from the outside they look very different. And the things that we were calling many-second laws, et cetera, were actually very closely linked to the fluctuation relations, and that we can see the connection between the many-second laws and what we sometimes call majorization relations and the fluctuation relations. So it was this kind of, what I want to present is this realization that what is happening underneath the fluctuation relations in stochastic thermodynamics is intimately related to something that we would call majorization. So it's noticing some mathematical similarity, I guess. So a mathematical similarity between what we often do in different fields and what's happening in stochastic thermodynamics. And then once you have this, kind of realization that these theories that different theories have some commonality, then it allows you to, in some sense, profit without doing any work. So for example, now that I know that majorization is what is behind fluctuation relations, I go to entanglement theory and I can discover an entanglement fluctuation relation. And I can now go and open up my textbook on applications of majorization and look for the fluctuation relations in all those different applications. So that's kind of, so those are kind of the 2 points I want to. Exactly. So you have, in information theory, we often think very abstractly in terms of a resource theory. And I guess the advantage of that is now that we understand the connection between different resource theories like entanglement and thermodynamics, we are now able to take the results from one field and find them in the other, and vice versa. So, for example, in the community of stochastic thermodynamics, people are interested in fluctuations around mean values and quantifying them. They often do measurements in order to do this. And in particular, they often, the notion of work has to do with measuring energy before and after. There's no actual work system. In quantum information theory, we've tended to model the work system explicitly. So the picture is identical. It's just that here we have an explicit battery. There's an implicit battery, and they use energy conservation to kind of say what the work is. So there's different paradigms, but they're kind of related. They're very closely related. And in quantum information theory, we are often interested in this thing called majorization, which I will try and explain, although many of you probably heard of it. And based on majorization, we had this notion of many-second laws, which I will try and explain a bit. And I'll explain the relationship between these majorization, these many-second laws, and fluctuation relations, and why they're very closely related. Good. And then comes the profit. Once you see that there's this mathematical underlying structure to many theories which is the same, you then can profit. So, for example, in entanglement theory, the thing that I think I've taken away after I've, learning something from the stochastic thermodynamics people, the thing I can take away is that I've learned that there's an entanglement fluctuation relation in entanglement theory, which is new. And I now think about entanglement batteries. Like in thermodynamics, we have work batteries which store energy, and it's a big weight. And now I start to think, oh, well, entanglement theory, we need to have an entanglement battery which stores entanglement and which we can use to do entanglement manipulations. So it's this kind of, these parallels that we see. Likewise, in entanglement theory, we had majorization criteria, and the thing that if we're thieves, we're stealing something from the thermodynamics community, the thing we're hopefully giving back is this notion that there are many second laws, there's many criteria which tell you whether I can do a state transformation in thermodynamics. Okay, so that's kind of that general outline of what I want to say. It's really just two key messages: connection between majorization and fluctuations, and the fact that now you can find, anytime you see a fluctuation relation, you can probably find majorization, and anytime you see a majorization relation, you can probably find a fluctuation relation. So we can now go through our textbooks and make discoveries. Good. So that's just the key two messages there. So majorization lies at the heart of Jarzynski and Crookes relation, and we can find fluctuation relations in it, and therefore we can find fluctuation relations in other settings. So let's start with kind of the most basic thing, just Landauer erasure. And if you ask people in quantum information about this, they will just say, of course, I understand Landauer erasure. Just KT log 2 bits of work is how much it costs to erase a bit. If you ask them some more detailed questions about that, then things get a bit more confusing. So let me ask these questions to you. So I don't. Here it's probably a different audience, but when I put the slide off in quantum information talks. So what do we mean by Landauer erasure, that it costs KT log 2 bits of work in order to erase a bit? Some quiz. Is A true, that it costs KT log 2 on average? That's what we mean, but there are fluctuations around this value. So how many people think this is true? Some people do.
It is true. We even measured it.
Yeah, okay. I mean strictly true, actually. I mean exactly true. So it's exactly KT log 2 on average, but there will be fluctuations around this value. We can achieve perfect erasure. How many people think that is true? There's a fight. You guys should fight.
Again, if you look at the nature paper with Sergio, you can approach it as closely as you want it.
That's a different question. Yeah, so we may be able to approach it, and then the question is how fast can we approach it, and questions like this. So, but can we actually achieve it exactly? That's one question you might ask. And then you might ask, can we use slightly more work on average and then sometimes gain work when we erase? Is that possible? You would say yes. Okay, so you would say yes. Then there's D. None of these statements are true. Now, if we include D, then it becomes a bit more problematic because maybe this quiz is undecidable. And the correct answer is actually that this quiz is undecidable, but not E, this quiz is undecidable. And the reason is that none of these statements are true. Okay? At least strictly true. And in order to know that they're not true, you actually need to go beyond the fluctuation relation and look at the majorization criteria, or at least the strengthening of majorization criteria, which is related to the fluctuation relation. So what we find when we consider majorization and this generalization of majorization is that, so the fluctuation relation in some sense tells us one thing. It's a single equation, right, about the fluctuations. It tells us something about the average of the exponential of work. But what we find, majorization is D criteria. So it's if a system of dimension D, it's D equations that need to be satisfied. So the fluctuation relation is one equation which has to be satisfied, but it turns out that there's actually D equations which have to be satisfied, and they're related to majorization. And when I average them, I get the ordinary, I don't want to say, I can say ordinary because Chris has not had to go home, but we get the Jarzynski equation when we average the majorization criteria. So there are in fact D criteria which tells us what will happen in any erasure process or any thermodynamic process. There's D equations which need to be satisfied. If we average them, we get the fluctuation relation, but their fine-grained nature gives us more information about what's possible. So in particular, when you work them out, you find that if I have an erasure process which succeeds with probability 1 minus epsilon, then I can plot the average work versus, say, how much work I get when I'm initially in the zero state. And what you find, for example, is that yes, you can achieve the average of kt log 2, but you can only achieve it when the fluctuations go to zero. So it's not true that you both can be on average kt log 2 and also have fluctuations. You achieve kt log 2 when there's no fluctuations. And what you also find is that if you want the erasure probability, the failure probability of erasing to go to zero, then the work fluctuations become larger and larger. So if we think about a physical system, like we imagine that we're, adding work to our system in order, pushing with a piston or whatever, if we want perfect erasure, then we have to be aware that there will be, with very small probability, these events which give us huge kicks of work. And so if our system can't handle those kicks, then there's always some tiny probability that we fail. Now that, for all practical purposes, that probability may be going to zero very quickly and quickly enough that we don't care about it. And that's certainly true for a bit, where it goes fast enough that we probably don't care about it. But for larger systems, when we're trying to put them in the ground state, this can have an effect and kind of gives you a third law in some sense. Okay. So that's kind of the outline of at least the first result. I'll try and present it a bit in more detail, but are there any kind of background questions, I guess? Yeah, good. Okay, good. So these are the two come from majorization, and I'll explain what majorization is. So the way I'll structure the talk is I'll kind of review kind of toy models of thermodynamics where we see what majorization is. And then I will talk about how that gives us the work fluctuation relations. And then, now that we have a connection between majorization and work fluctuations, I'll then talk as much as I can about how it happens in thermodynamics. And in entanglement theory. And I'm aware that most people here are not from the entanglement theory community, so we'll see how it goes, and I may not get to that part of the talk as much as I'd like, but I'm happy to talk about it after. Okay, so here, don't get put off by the slide. I'll try and explain it in a more intuitive way. But what we find is that there are more kind of gradually increasing notions of majorization. So the most basic majorization, which was discovered by Hardy, Littlewood, and Polya, is about what we call doubly stochastic maps. So we imagine you have some probability distribution. So you imagine we have a system. It can be quantum or it can be classical. And we have probabilities of having a particular energy level S. All right, so a probability distribution over energy levels. You can see here we're doing a kind of a thermodynamics where we imagine that there is a density matrix. So people sometimes don't like that. Some people do. And the thermodynamic transition is just going to be given by this matrix which acts on the initial distribution and produces the final distribution given by S prime. All right? So we start off with some initial distribution. We act a map on it. We get a final distribution. And a map is doubly stochastic if it preserves the identity. All right? And that's when you have doubly stochastic maps, then you start talking about majorization, because the majorization essentially says that I can go from one distribution to another distribution via a doubly stochastic map if and only if the distribution of S prime is majorized by the distribution of S. And I'll give an example to make that very intuitive. So we're going to start with some kind of this basic notion of majorization, then we'll get to a kind of a more, one that's more relevant in thermodynamics, where we have a Hamiltonian, which we sometimes call thermomajorization or demajorization. And then when we add fluctuating work, we get a different notion of majorization. Okay? And this is the one that will lead to the fluctuation relation. So let's talk about majorization, and we'll do it I'll try and explain it in a very intuitive way. We sometimes call this thermodynamics for children. Robert will like it because it's just Szilard boxes. So imagine I have this Szilard box here. So it's a partition with the molecule being either the left or the right. And let's imagine that it has a higher probability of being on the left, all right, because of some process. And the game is I want to transform, this is kind of a state of the box, right? The state of the box is the probability distribution of being in the left and the right. And imagine I want to transform it to this Szilard box where the probability on the left is slightly smaller. And the game is I am not allowed to add work to my system. All I can do is remove partitions and put them back. All right? And the question is, how can I go from this box to this box? Or this distribution to that distribution? And when can I go from it? So does anyone want to maybe guess or say how I would go from this box to this box? Or this distribution to this distribution is a better way of saying it? All I can do is lift my partition out and put it back in. Yeah. So don't bother asking. Yeah, so obviously what I'll do is I'll lift the partition for some time and put it back in. Or if I don't know the diffusion time, what I might do is, so this is I just lift it out, let it diffuse a bit, and then put it back in. If I don't know the diffusion time, what I could do is I could put in another partition here, then remove this partition, let it equilibrate, and then put the partition back in. So I can do it without really knowing the diffusion rate. And now I want to know, given this probability, let's imagine I have a Szilard box with many partitions, can I go from this distribution, so the probability of being in the first box is 1, the probability of being in the second box is P2, P3, P4, and I want to know, can I go to this distribution, Q1, Q2, Q3, Q4? When can I do it? You won't be surprised that the answer is if and only if majorization. Okay, so I can only do it, so what I do is I take all the probabilities in the first box and I order them from largest to smallest, and I take I look at the second box and I also order them from largest to smallest. And now I ask, if I add up the k largest probabilities in the top box, are they larger than the k largest probabilities added together in the bottom box? Okay? And if that's true, then I say that P majorizes Q. And very intuitively, you can see why this gives you the criteria for being able to go from this distribution to that distribution, because I'm going to do these processes where I lift up the partitions, let some diffusion happen, and then put the partitions back. And that's called a Robin Hood process. I think this was even called Robin Hood processes by Hardy, Littlewood, and Polya. There's also called T-transforms. But you can see it's a robbing of the rich to the poor, right? So this is the rich one, it has the largest probability, and so I take a bit of this probability and give it to this person. And then I'm going to rob from this P2 and give it to the third box. And then I'm going to rob from the third box and give it to the fourth box. And I can only do the robbing from the rich and the giving to the poor if the sums of the k largest probabilities in the first box are larger than the k largest probabilities in the second box. The arrow means that I'm ordering them from largest to smallest. So here I've just arranged them and just reordered them, called this P1, P2, P3, P4, and it doesn't cost any work. If I imagine frictionless surfaces, it doesn't cost any work to rearrange the boxes. So I just rearrange my boxes so that the probability of the largest of being in this box is the largest. And now I rob from the rich to give to the poor to get to this distribution. Okay? So that's the majorization criteria. And you can see that in this thermodynamics for children, it gives you the criteria of whether you can go from one state to another. All right? And you can also see how it's related to doubly stochastic maps. So remember, doubly stochastic maps are maps which map the identity distribution to the identity distribution. So I can keep doing this process, but eventually all the probabilities become equal. That's the identity distribution. And once that happens, there's nothing I can do. Removing partitions does nothing, doesn't change the distribution. So the identity, the uniform distribution, is the fixed point of these Robin Hood processes. And so I can look at these maps as being the maps which preserve the uniform distribution. All right? Is there any questions about that?
So the quantum version is a unity map, right?
That's right. Yeah. What I'm going to tell you here, although I'll start talking about entanglement, these things apply to entanglement theory. What I'm talking about is very classical. I have some other quantum things, but I've removed most of the quantum things from this talk to kind of simplify it as much as possible. So one can derive quantum fluctuation relations, things that look, quantum identities which look like fluctuation relations is probably a better way of saying it. But here I'll be talking about very classical things. Okay. So here are these general transformations. So I robbed from the rich. So this is the way I was saying. I want to start from this distribution here and get to this distribution here. So what do? I put in a partition, remove this partition, let it kind of equilibrate, and then put the partition back. And that kind of moves probability along. And I can only do it if the majorization criteria is satisfied. Right. And this corresponds to, we call this version of thermodynamics for children, we've been calling it noisy operations. And like I said, it corresponds to, in the classical case, doubly stochastic maps because they are, so you can think of the theory as follows. I have my system, I bring a heat bath, which in this case is the uniform distribution. I'm allowed to perform any unitary, and then I throw it away. And I can ask what possible distributions are possible. And it's exactly the same as the Szilard box theory. It's just given by majorization. So the Szilard box theory corresponds to a kind of toy version of thermodynamics where I don't have any Hamiltonian and where I'm allowed to bring a heat bath at infinite temperature, interact with my system, and throw it away. No. So it's a partial ordering, and in fact, in most cases, you'll often have the situation where you have two states and neither can go to the other. But then you can start to ask questions like, how much work do I need to add before I can go? So that's what we'll get to. We're building up to that. We'll start saying, well, how much work do I need to add to get this to majorize?
There's no single number to decide.
Right. It's D. That's the kind of the point. There are D criteria which have to be satisfied. One for each. For each partial sum, that gives you D criteria. So that is kind of the point. This is why we talk about kind of many second laws. Instead of having just one criteria, the entropy, whether you can go from one state to another, there are these D criteria. So, I mean, notice...
But it does have a maximum element, right?
Sorry?
It does have a maximum element, right? Even though it's a partial order, there is...
Right.
The uniform distribution is the maximum element.
That's right. So the uniform, and then if P is 1 for one particular item, that is the most powerful state. But notice something here, which is that, the entropy it doesn't seem to be appearing here, right? So usually we would say we can go from one state to another if the other state is more mixed with it, if the entropy is larger, if the entropy of the gray molecule is smaller than the entropy of the blue molecule, then we could make the transition. That's what we would normally say. But here we see that we have more strict criteria. Now, but the entropy does emerge. So if we were to take many copies of this, so like in a non-interacting gas, if we have many such boxes, then it turns out that the majorization criteria becomes equivalent to just the entropy criteria. Okay, so for finite size systems, you get this majorization criteria, but if I look at many such systems, and I have many of them, like in a gas, then the entropy is the only one which survives, right?
It's a criterion of accessibility. I mean, what is it a criterion of?
For state transformation. So can I go from it, right? Just the question: can I go from this to the other? And I think some people will disagree, but I think of the second law as just being a accessibility criteria. It's more than that, of course, but one of the things it does is it's an accessibility criteria. It says, can I go from this state to this state? And I can do it if the free energy goes down, or I can do it in this, if the entropy goes down. goes up. So it's just basically a criteria for accessibility. And what we're saying here is there's actually D criteria for accessibility, if D is the dimension of the system, but in the thermodynamic limit, they all become equivalent to just the standard free energy. Okay. Good. So now let's go one step up. We've been doing a thermodynamics for children. We're going to do, I think, what some people would also consider a kind of thermodynamics for children, but it's a slightly, at least we have a Hamiltonian. So what we're going to do is we allow a Hamiltonian. And then we kind of know that before what we were looking at were maps which preserve the uniform distribution. Now we're looking at maps which preserve the Gibbs, the thermal distribution, right? In some sense, you can think of it that as being a definition of thermodynamics. It's if I don't have a work system, then thermodynamics are just all the operations you can do which preserve the thermal state, because that's a version of the second law, right? That if I'm stuck in my, and you present it as one where you know, it's a nice one because it just says it's the kind of a minimal one. You just say, if I'm in the thermal state, I have to stay in the thermal state. I can't get out of it. And that's true if you don't have a work system. So this is kind of slightly more sophisticated. It's basically just that version of thermodynamics. So if you look at this, what this says is the first condition just tells me that probability is normalized. So I'm going from distribution S to S prime, and this just tells me that I must keep normalization. So my transition probability matrix has to sum to 1 if I sum over S prime. And if I sum over S, that's like saying that I'm acting this on the Gibbs distribution and I get back the Gibbs distributions, or the thermal distribution. So this criteria here just says you need to conserve probability, and this criteria here says that I have to preserve the Gibbs state, the thermal state. And so that's a slightly more, we're moving away from thermodynamics for children to like thermodynamics for young adults. Okay. And if you, did anyone have a question about that? That is a definition of a kind of thermodynamics where I just say if I don't have a work system, I can't get out of the thermal state. That's a definition of it. I can do everything. I'm not do whatever I want as long as if I feed in the Gibbs state, I have to leave with the Gibbs state.
So is it not the same as just detailed balance?
No, it's stronger than detailed balance because I'm allowed to have strong coupling. Yeah. Yeah, so it's not for any, it's just, has to be true for all S prime, but that's it, right? So again, it's D criteria. So this is D criteria. So you have more criteria than the fluctuation relations. You have D of them. Right. It corresponds to this. So we want to have definitions which are as broad as possible. So saying that we allow everything that preserves the thermal state, that's a very broad definition of thermodynamics. It's a good one if we want to derive limitations, right? Because we want to we're paranoid, we give the experimenter the most power they can possibly have, even if they can't even use it. We know that they'll never be able to do all these things. And then if we derive a limitation, we know it has to be true, right? They won't be able to get around it. As long as we've been paranoid and giving the experimenter the broadest possible definition of thermodynamics. So, operations which preserve the Gibbs state is a very broad definition. It turns out that there's another one which is equally as broad. It's called thermal operations. It has a long history, and it's kind of been added to in some sense. And I guess what I just want to say about it, because we could have a whole discussion about this, but it has one main component. One is that we demand that energy is conserved. And total energy of all my systems and everything. In stochastic thermodynamics, there's the same assumption, but it's hidden. So in stochastic thermodynamics, when people measure the energy before and after, and then call that work, what they're assuming is that there's an implicit work battery, and if I were to conserve energy, all the energy that is removed must have appeared in that work system. Okay, so it's an implicit assumption in the stochastic thermodynamics community, and we here make it very explicit and put in our work battery, but it's effectively the same kind of assumption. Okay. And we're going to add an additional an assumption. We're about to do that because we want to talk about fluctuations. We're going to add in a work system, And what we're going to demand is that the amount of work we extract into our work system, the amount of energy that ends up in our work system, does not depend on how much is already there. Again, that's an assumption that's implicit in the stochastic thermodynamics community. So they just say, I measure the energy before and after, whatever that is must be the work. So work is the raising and lowering of my weight, for example, or the lowering and raising of the energy in my battery. And I don't care how much was there initially. I just care how much I'm adding or subtracting. All right? And so we make that assumption and make that explicit. Is that clear, that assumption?
Sorry, I'm just going to follow up. The weight here can be arbitrary, or is it a continuous medium, or does it have some spectrum?
So all you really need is that for any transition you want to do, it has to have the right energy levels. Saying that it's continuous doesn't hurt, and is what we...
If you're trying to map out the fluctuations of work that's done in the system, then somehow if you mismatch in energy,
right.
This is a problem, right?
Yeah, so you have to assume that you have an energy spacing of your work system which is enough to kind of commensurate with all possible things. So the easiest thing is just to take it to be a continuum, harmonic oscillator or something like that. Okay, so this is what we're calling thermal operations with work. Okay. I think we used to have a WIT, which was a two-level system, and if we want to really look at fluctuations, we need to have this continuous thing. So I think this is kind of a
You're saying thermal operations with work?
Well, I think we used to have so when I remember I gave you that Zillard box theory where all I'm allowed to do is move the partitions. Now I want to add work into the game. I'm allowed to add work. So I now consider a work system. I can model it implicitly or explicitly, but the important thing about a work system is that I say that the energy that's not in my system in Bath has to go into the work system.
So it's just energy conservation?
It's just energy conservation, which is true. I mean, energy conservation is not a law of thermodynamics, it's a law of nature. Right. Yes. And then the other thing is that I don't care about how much, if I want to call it work. So there's a couple things you might demand for a work system. One is that you don't want to throw entropy, you don't want to cheat. You may be able to cheat by throwing entropy into your work system. And you don't want to do that. So one way of enforcing that is to just say, I demand translation invariance. In other words, I demand that so it turns out that if you demand translation invariance, then you will not be able to cheat in this way of throwing entropy into the work.
Well, for mechanical work,
yes.
It can be other kinds of work.
Yes, and in fact, we've been.
What does it mean, translation invariance?
So so in the stochastic thermodynamics community, it's saying that the work. So in stochastic thermodynamics, what they do is they measure the energy before and after, and they say work is the difference, and it makes no reference to how much energy was already stored in the battery. So if my definition of work should not depend on how much energy was stored in the battery previously. So it's implicit in the stochastic thermodynamics community because they just say whatever the energy difference is, we consider that to be work, and then you don't need to.
Is this the same as momentum change?
No, there's no structure at all. There's no momentum. There's nothing.
We can imagine, let's imagine like just a ladder, a doubly infinite ladder, say, where the work is just, like lifting a weight. So just lifting up the weight. And what we demand is that our operation, whatever our operation is, it has to not depend on where the weight is at that particular point. So it's like for a battery, we want to just put in the battery is about, work is about how much we raise the weight. It's not about where it is. It's the difference. What we care about is the difference. That's what we want to say. So it's implicit in almost any destruction, it's implicit in any notion of work, but we want to make it explicit because sometimes we like to have I like to think operationally where I actually have this work storage system there.
Well, what if you have chemical work?
Right. So we've also looked at the case where you have.
Because you have some translation by some commutation relations.
Yes.
What is delta?
So, sorry, yeah. So because of the length of the talk, I haven't had a chance to kind of go through the details of everything. And I can do this, means we won't have much chance to talk about entanglement, but let me first answer your question, which is you can have different batteries for different kinds of work. Like you can have angular momentum battery, you can have chemical energy. We've also looked at the case where they don't commute. The different kinds of work don't commute. So in a classical system, you might have a grand canonical ensemble where you have e to the minus beta h minus mu n minus mu 2 some other thing. Those things are always assumed to commute. But what if they don't in the fully quantum case? So you can imagine different kinds of work, some of which don't commute with each other. So you can have different batteries, and then you might want to say, what does it mean for this battery to be a work battery and not a chemical battery? And what you mean is that you can only raise or lower the amount of energy. You can't change the particle number in it. Likewise, what do you mean for a battery to be an energy battery and not an entropy battery? It means you can change the amount of energy, but you can't add entropy into the battery. So that's what this thing enforces. So yeah, these are the raising and lowering operators, and we just mean that it commutes, your operation should commute with raising and lowering. So in other words, we just care about the difference in energy of the weight. If someone goes and raises the weight, we do our operation, and then they lower the weight, it should be as if they never interacted.
The second commutation can be only satisfied if those operators are unbounded from below.
That's right.
So this is against the basic
That's right.
principle of stability.
That's right. But it's the same. But that's also but you see that when you see, this is what becomes interesting in my view. That assumption is what's made in the stochastic thermodynamic community. So they basically just measure the energy before and after and say the difference is the work. And that could be unbounded. So there's no bound there from above or below. So now, of course, in a real system, what you would have is you would have a lowest energy level, and then this would be only true as long as you were far enough away from the ground state. So you can get around that by imagining that you're high enough away that you never reach the ground state. But that's an assumption. And that's what you get when you kind of try and make the system concrete. You realize that this notion of work as being the difference in energy before and after is only true as long as you're far enough away from the ground state of your battery. And as soon as you're near the ground state of the battery, then things become a bit, things start to change a bit. And in fact, change the fluctuation relation in a real system. Okay.
Does translation invariance actually imply that it's always independent of the works, of the state of the work, the extracted work, or does it only hold for diagonal states?
Good question. It's a very good question. So it means that it could depend, our operation could depend on the state of the weight. So demanding translation invariance is a weaker assumption, and we allow it to depend on the state of the weight. And so, for example, if we want to do a coherent operation, then we will need a weight which is in a superposition, and then, if you have a weight which is in a superposition of different energy levels, you can do a lot more. You can do coherent operations, and if it's not, then you can't. It's a good question. Maybe after we can take the questions on the paradigm, which I think are good ones, and move on for the moment. Okay. So here you see that work is just, in the classical case, work is this weight which raises and lowers, and when we just imagine that we're far enough from the bottom of the cliff that we never need to worry about it hitting the bottom of the cliff. And likewise, we're just going to imagine that we have a ladder system of equally spaced levels that are very dense, and we are high enough away from the top that we kind of never hit the bottom. So it's just an idealization, but in a real system you would have this thing. And as far as we know, this is the broadest possible definition of thermodynamics we can imagine, because we want to derive limitations. So we are paranoid. We make sure we include any possible or as many possible definitions of thermodynamics as we can. So for example, it includes the situation where you add an interaction Hamiltonian. It includes the situation where you have a time-dependent Hamiltonian. You just have to add in what we sometimes call catalysts. As Robert points out, it we imagine that initially we're uncorrelated, our system is uncorrelated with our bath, or at least we don't exploit the correlations if they're there, so there's that assumption as well. But, as far as we know, this is kind of the broadest possible definition we can imagine, which can still realistically be called thermodynamics, and we use it because we want to derive fundamental limitations, all right? We might later then ask, are there a simpler definition of thermodynamics which would allow us to be implementable in the lab? That's an interesting question, one we're interested in as well. But if we're trying to derive fundamental limitations, we want to give the most power to the experimental as is possible. And then I can just give you the punchline. This corresponds to operations which preserve the Gibbs state, and so you have this kind of thermomajorization rather than majorization, and it corresponds to a whole family of free energies which happen to look like this. They give you a distance to the Gibbs state. There are many different kinds of distances to the thermal state, the Gibbs state of the thermal state. And they give criteria on whether we can make a transition from one state to another. Okay, so instead of having the majorization criteria, we get these new free energies which provide criteria for whether we can go from one state to another.
The actual free energy,
Corresponds.
which state is
That corresponds to alpha equals 1 in the limit alpha equals 1. And if you take the thermodynamic limit, all of these actually end up corresponding to alpha equals 1. So alpha equals 1 is the ordinary free energy, and in the thermodynamic limit, all these F alphas correspond to F1 and give you back the ordinary free energy. Okay. So now I want to add in work to get the work fluctuations. All right. And so we've gone from majorization criteria, which was this little Szilard box toy theory, to thermomajorization, where instead of preserving the uniform distribution, we now have to preserve the thermal state. And now we add in fluctuation work, and we get a slightly more complicated distribution. It turns out that we can make a transition if and only if we can find a P such that this is true. Right? And you can see it looks like thermomajorization, but it has this W random variable sitting here. Okay? So now instead of having a majorization criteria, we have this criteria, which is a kind of a generalization of majorization. And notice again, it's D conditioned. So if I want to know if I can go from one state to another, I now have D criteria, which tell me whether I can do it or not. And so it gives more fine-grained information about whether something is possible in thermodynamics. And that's why I would say this is like a second law with fluctuating work. And now comes the cute thing. If I take this, so this again just expresses the fact that probabilities have to stay probabilities that are normalized. And this expresses the fact, kind of a generalization of preserving the Gibbs state, the thermal state. And now what I find is if I take these D conditions and average them, I get the Jarzynski equation. Sorry? Right. So this just expresses normalization. I could have put W in sum over W. It wouldn't matter. So this just expresses the fact that I conserve probability. So the probability of going from S to S prime, if I fix S and sum over S prime has to be 1, because this is just like saying you have to go somewhere. Okay. And then this expresses the kind of a generalization of conserving the Gibbs state. So if I didn't have the W, it would be preserving the Gibbs state. And if with the W, it's some kind of generalization of it. I don't know what to call it. Okay. And now, but let's take it here. Let's multiply on the right and the left the final probability distribution, P of S prime, and then let's average over S prime. Okay? Something we can do. So we take our D conditions, we average it to get one condition, and what do we get? We just get this Jarzynski-like equation over here. Okay? It's a fine-grained Jarzynski equation in the sense that I don't need the initial or the final distribution to be thermal, so it works for all initial and final distributions. But it's a Jarzynski equation. So you get the fluctuation theorem as a average over all these majorization-like criteria. Okay? This is, I should say that this generalization of the Jarzynski equation has been, we thought we were special, but it is actually derived, or at least appeared in 2012 and probably known before then by Sagawa and Seifert.
Sorry, how do you define this W?
Work.
In any of those relations?
Okay, so the way we derive this relation is just coming from, we derive it by basically just looking at this definition of thermal operations and say, when can we go from one state to another? We derive it as a criteria. So W is just given by, the change in energy of the work system.
Just change in energy.
That's right.
So you may, count the heat for work.
No, so we're imposing translation invariance, and by imposing translation invariance, you see that you don't get any heat.
Okay.
I mean, what you're able to derive is if you're translation invariant, then your operation on your system corresponds to a mixture of unitaries. So you can prove that. So that is kind of like saying that translation invariance kind of imposes what you might think of as the second law. Because if all you can do is a mixture of unitaries, then you cannot pump your entropy into the work system. There may be a weaker definition, which also
I'm keeping, asking myself whether this is unique in some sense.
right. Good question, and I don't think so. So there may be a weaker definition of thermodynamics which still preserves the second law. Yeah. No, I don't think you can do whatever you like, but there may be a weaker version. I mean, the weaker version that we have actually also leads to the same relation, so I don't think that there's a thing there. But proving that is, okay, one should do that. But yeah, I agree that that is a good question, and one should answer that. Good. So what we find is that we can derive this generalized Jarzynski equation, and as of course you know, what this is just corrections to the standard. I more give this slide when I'm talking to the quantum information community, but this, the Jarzynski equation, we can think of it, or especially this generalized one, as a more sophisticated version of the second law. So we're used to saying that the free energy, that the work that we put in has to be less than the average free energy. And what we find is a random variable here which quantifies how much the work exceeds or doesn't exceed the change in kind of fine-grained free energy as a random variable. And so instead of just having a second law which is about average quantities, we have all the higher moments and corrections. You can think of these as corrections to the average value statement of the second law. So we have a more refined version of the second law.
But f is not, lowercase f is not a scalar, it's a vector, no?
It's a vector, yeah. So for every s, it's basically just the kind of, if you were to average f, you would get the free energy. So it's just E plus T log P for a particular s. And we call it a fine-grained free energy. If you average it, you get the ordinary free energy. It may be related to some of the stuff you were showing in terms of this, like log, I don't know, the log of the density matrix as the kind of operator that you were interested in. Okay, so let me...
No, it's just, we have the end somewhere.
Okay, good, we have the end. So let me, I didn't get to the entanglement case, so I will just say what it is and it'll be the end, I promise. So all I'm saying is now we have that we see that fluctuation relations have it behind them majorization. And in entanglement theory, what we knew is that Alice and Bob, who share an entangled state, can go from one state to another if and only if majorization. Okay, that's what we knew. Goes in the other direction as thermodynamics. And so we were like, now that we know that fluctuation relations are about about majorization, we should be able to find a fluctuation relation for entanglement transformations. And so what did we do? We were able to do that. What we were to do is, instead of having a work system, which is a weight, we have an entanglement battery, which is just a system which has E-bits in it. It has a number of E-bits, and you can add E-bits or take E-bits away, and that is like the work. It's like an entanglement work system. It's an entanglement battery. And now we find that we can do all kinds of things that people do in thermodynamics. So we can, for example, do single copy transformations. We don't need to have, there's a whole bunch of things you can do now in entanglement manipulations, which we can basically take from thermodynamics. So that's kind of the profit. So with that, I won't go through the details, but I'm happy to talk about it. And just to say that we have kind of a Crookes relation for entanglement. We have reversible entanglement transformations and reverse transformations. We have this Jarzynski equation where instead of having a free energy, you have a dimension. And we have this generalized second law of entanglement transformation. So we've kind of made entanglement look like a thermodynamics, which kind of we knew was lurking there from previous work, but this kind of really gives the full, I think, picture. So in summary, just pure state entanglement criteria is like the second laws of thermodynamics, many second laws. Work fluctuation theorems are like entanglement fluctuations. And then now there's the question, can we find these things in other, because majorization is so ubiquitous, can we go around and find these things everywhere? There's a textbook called Majorization and its applications. It's 800 pages long. I feel like there's a lot of work to be done. And thank you very much for your attention.
So we have had already plenty of questions. There's another one, but we have to restrict the questions to maybe two or so.
A very nice relation where you see the F's as random variables and then the average. Is there a quantum version of that particular thing? Because that would be very like this fine graining that you do classical mechanics and quantum mechanics. It's at least not obvious because you have random variables.
So you can, but the interpretation is stranger because in the quantum case, kind of everything happens. So you might think it wasn't as easy to go from the thermodynamics to the entanglement because that's a difference. You don't have, for a battery you can measure the work before and after, and here you cannot measure your entanglement battery because you would destroy it. So in some sense, you have this quantity, but it's physical interpretation. You could measure it, but you would destroy the system if you did. So maybe there's more to be had there, but what's nice is it's truly quantum, so it becomes kind of more interesting in some ways. Great.
More questions?